Here we will look at electromagnetic waves, which are more familiarly known as light waves. Electromagnetic waves are a class of waves that are transverse, which all travel at exactly the same speed in a vacuum. This speed is 300 million meters per second, more commonly known as the speed of light. In the last video, I stated that the speed of a wave is equal to its wavelength multiplied by its frequency. Since we know the speed of all electromagnetic waves is the speed of light, we can describe an electromagnetic wave just by its wavelength, since from that we are able to deduce its frequency. If the wave has a large wavelength, it must have a low frequency, and if it has a small wavelength, it must have a large frequency, since the product of the two must always be the same, the speed of light. Electromagnetic waves can have a huge range of wavelengths, going from 100 meters plus all the way down to less. We classify the different types of electromagnetic waves by their wavelength. The longest wavelengths are known as radio waves, and as we get shorter, we go through microwaves, then infrared waves, then visible light waves, followed by ultraviolet waves, and then finally X-rays and gamma rays. Why do we call this segment here the visible light segment? It is because this is the range of wavelengths that our eyes are able to detect. Detecting them and then sending signals to our brain that create a visual interpretation for what is being detected. This doesn't mean that other electromagnetic wavelengths don't hit our eyes. It just means that our eyes aren't designed to detect them. We have, however, created new ways to detect these other wavelengths other than with our eyes. And telescopes, night vision goggles, and Geiger counters all do just this. The visible light section makes up so little of the whole electromagnetic spectrum, and so we must build machines that can see the rest of the light in our universe. Our eyes see but a slither. Within the visible spectrum, we find that our brains interpret longer wavelengths as red light and shorter wavelengths as blue light, with the spectrum of colours in between. We have applications for the whole range of the electromagnetic spectrum, and a few uses and potential dangers are listed here. Sound waves can't travel in a vacuum, but we are able to calculate its speed in air. We again find that our ears are only designed to detect a certain range of sound waves. This time we will talk in terms of frequency, and we find that our ears are only designed to detect sound waves with frequencies between 20 and 20,000 Hz. Our brains interpret high frequency waves as high-pitched noises and low-frequency waves as low-pitched noises, and the loudness of a sound depends on the amplitude of the wave.